Good afternoon. So I'm Yaswanth from IT Madras. I'll be concentrating on utilizing different remote sensing satellite precipitation products for improved flood accuracy. So rain gauge typically measures a point rainfall, but if we can consider satellites and weather radars, it can measure a huge area. For example, satellite can measure quasi-global to global, as well as the weather radars can measure and having a range of 250 kilometer to 300 kilometer range. So how can we improve these rainfall products so that the improved flood accuracy can be achieved? So during my PhD, I have concentrated on several satellite precipitation products, which have a latency of an hour to 4 hours. And I have found mostly the iMerge final precipitation developed by NASA is having a better performance, as well as we have also utilized weather radar product provided by Indian Meteorological Department. So focusing on one of the extreme precipitation event that has occurred in Chennai, the Southern Peninsula region in India, it has caused an $4 billion loss. So approximately in 2 days, accumulated rainfall has varied from 500 mm to 300 mm in the city urban zone. So these rainfall values typically dictate the spatial variability that is present. So capturing the spatial variability is highly important if we need to generate an improved flood hydrograph. So if you see from Doppler weather radar, the GPM and different satellite precipitation products are showing different spatial variability, but we can reduce this bias using the observed rain gauge. So typically to correct this bias, what we have done is we have calculated the ratios between the gauge and satellite and interpolated these ratios to each and every grid point so that these bias can be multiplied with the satellite precipitation products and can generate and improve high resolution rainfall products. And at the same time, in the developing countries, we have mainly a daily rainfall measurement, but not at sub-daily scale. So using the temporal distribution of GPM satellite rainfall data, we have tried to disaggregate the daily data into off-hourly rain rates. So we typically noticed an improved performance when we have done such kind of analysis. So we can see the disaggregated gauge rainfall and the hourly rainfall measured by the station. So the both are matching pretty well. And the generated hydrographs are very closer when I have used the disaggregated rainfall data rather than the rainfall data from the daily scale. So when it comes to other application of high resolution remote sensing precipitation products, so we have recently implementing numerical weather prediction models at high resolution. So generating the rainfall at 1 kilometer forecast. So at 1 kilometer forecast, running a numerical weather prediction model requires high supercomputing power. So we need different combination of physics options, and among these, which physics combination is giving a better rainfall forecast should be identified. So if we consider different physics combinations that the rainfall maps that I have generated, the first 4 shows the satellite data with and without bias correction, as well as different combinations. And you can see the highest rainfall has happened in the southern regions of the basins. And typically the bias corrected GPM and radar data are able to match with few of the combination. So I could select which combination of physics options are giving better rainfall forecast. For example, CO6, CO7, and CO8. And if you see, some of the simulations are with urban canopy models. So when we focus mostly on local flood elevation mapping, urbanization can change the rainfall spatial pattern because of urban heat island. So we have made different combinations with single layer urban canopy model, multi-layer urban canopy model. And with the forecast, we have identified that the multi-layer urban canopy model are giving better precipitation forecast than the single layer urban canopy model. So again, to the another event, which has nearly downpoured 200 mm of rainfall in just 6 hours, we have again noticed that the single layer and multi-layer urban canopy models are generating better forecasts, and we are able to compare with the bias corrected GPM precipitation data. So this all just tells the importance of satellite precipitation products when we are generating high resolution forecast. And typically the other application, major application I could find with the remote sensing precipitation products is the generation of intensity, duration, frequency curves. So generally this requires hourly rainfall data or sub-hourly rainfall data. But typically in the developing countries, again, we have lack of sub-hourly and hourly data. So if we compare with different satellite precipitation products, so we have generated return level maps for 2-year return period until 100-year return period from short duration to long duration using multi-source weighted ensemble precipitation, Persian data, GPM, and others. And now we are trying to use multifractal property or or else machine learning techniques to merge these with station data so that we can develop a high resolution intensity duration frequency course across the India. So typically these multifractal properties developed at hourly gauge stations. We are trying to interpolate this using kriging with external drift to the entire India to generate the high resolution intensity duration frequency maps. So essentially, if you see the diverse application of remote sensing rainfall projects, so we can have an improved hydrological models. We can use this for generation of high resolution intensity duration frequency curves or improved hydrologic modeling as well as for nowcasting. Thank you.